Welcome to our lesson on operations on functions. In this lesson, we're going to be finding both all of the sum, difference, product, and quotient of functions, which is something that you're used to doing. There's nothing real surprising there. But the new concept for this video will be to find what we call the composition of functions. So let's start off just by giving some definitions here. Function operations. If we have two functions, say f and g, we can add those two functions, we can subtract them, we can multiply or divide them using our standard rules of arithmetic. And I've given you some formal definitions here and also some examples given two functions f and g. The only thing I want to mention here is that when you're doing the quotient of two functions, you do need to define values that are not included in the domain. And those values are what makes a denominator 0. So to find the value that would make the denominator 0, you set the denominator equal to 0 and solve it for the variable. And that tells you what number is excluded from your domain. So for addition and subtraction, I have a couple of examples here. We've got a function f and a function g, and we want to find the sum and the difference of those two functions. So the sum of the functions is just taking the two functions and adding them together. To do that, we need to add our like terms. So 5x and 3x will be added to give us 8x, and negative 2 plus negative 2 is negative 4. So that's the sum. The difference, very similar. We're going to take 5x minus 3x, which will give us 2x this time. And negative 2 minus a minus 2 is negative 2 plus 2, so that term drops out completely. When we're multiplying, we're going to be using the distributive property. So I have the two functions here. When we multiply, we're going to take the first term times the binomial, then the second term times the binomial, and the third term times the binomial. And we'll use our distributive property on each of those. And then combining our like terms, we end up with 3x cubed plus 13x squared minus 16x plus 4. And then dividing, we're just going to take the first function f on top of the second function g. Again, x equals 2/3 is not in our domain because that would make our denominator 0. Remember, set this equal to 0 and solve for x. You would add 2 to both sides, then divide by 3, and you would get x cannot equal 2/3. That is not in the domain. So here we go with composition of functions. Composition of functions is basically just applying one function to the results of another. The range of the first function becomes the domain of the second function, and this gives you a third function then. Okay? So the symbol for composition is this open circle. It almost looks like a multiplication sign, but it's open, not solid. And the algebraic definition is this: f composite g of x is equal to, and we read this thing right here as f of g of x. F of g of x. So let's look at some examples. Suppose we have this function f and this function g. So f is mapping 3 to 4, 2 to 3, and negative 5 to 0. So if we want to find f composite g, we start with the function g. So the domain of g, remember the domain are the x values. The x values are 3, 4, and 0. So here is our domain. Now the function g maps 3 to negative 5, maps 4 to 3, and maps 0 to 2. So the range is negative 5, 3, and 2. Now that range of g becomes the domain of function f. Those are outputs for function g. They become inputs for function f. So we want to know, what does function f do with negative 5? Well, function f right here takes negative 5 as an input and maps it to 0 as an output. So we'll get a 0 right here. What does it do with 3 as an input? It maps 3 to 4 and it maps 2 to 3. So we will get outputs, or the range, of 0, 4, and 3. So now we can say f composite g is equal to an input of 3 gives us an output of 0, input of 4 gives us an output of 4, input of 0 gives us an output of 3. And so we just write those as ordered pairs. Similarly, if we want to find g composite f, we start with function f, the domain of f. So our domain is 3, 2, and negative 5. it maps each of those to these values. So this is now the range of function f becomes the domain of function g. So now we have inputs for function g. And function g maps 4 to 3, 3 to -5, and 0 to 2. So there are our outputs. So to write the composition function, we have an input of 3 gives us an output of 3, input of 2 gives us output of -5, input of -5 gives us an output of 2. The composition of two functions may or may not exist. The composition of two functions f composite g is defined only if the range of g is a subset of the domain of f. Okay? You also may notice in our last slide, f composite g was not equal to g composite f. Okay, so switching the order of composition gives us different functions. Another way of saying that is composition of function is not commutative. The order matters. So here are some more examples. Here's function f and function g. They want us to see if f composite g and g composite f exist. Well, let's go ahead and start with f composite g. So we're going to start with function g. Function g has inputs of 5, 3, 7, and 9. So I have those right here, 5, 3, 7, and 9. Those are on the inside. We're going to see what that gives us as an output. So function g maps the number 5 to 7. So that's going to become an input for function f. So function g maps 5 to 7, but what does function f do to 7 as an input? It maps 7 to 8. So the output is 8. Function g maps 3 to 5. So then we're going to take 5 and use it as an input for function f. Function f maps 5 to 3. So 3 is our output. Likewise, g maps 7 to 9, and f maps 9 to 8. G maps 9 to 11, and f maps 11 to 4. So now we can take our input of 5 and say it goes to 8, 3 goes to 3, 7 goes to 8, and 9 goes to 4. So f composite g is equal to this function with this set of 4 ordered pairs. Well, let's take a look at g composite f now. If we want to do g composite f, we start with function f. Function f maps 7 to 8, but there is no 8 in the domain here. It doesn't exist in function g, so we say g of 8 is undefined. Well, how about f of 5? That's our second element. It maps 5 to 3, so we need to find g of 3, and g maps 3 to 5. So that one we actually get a valid output. Function f maps 9 to 8, okay? And so we need to look again. We said g of 8 is undefined. That's that same thing there. Function f maps 11 to 4, but again, there's no 4 as an input for function g, so that is undefined as well. Now what happens is when you have these values that are undefined, the composition function would be undefined except for we did get one valid output. So since 2 of our values were not in the domain, g composite f is undefined for those 3 input values, f of 7, f of 9, and f of 11. However, we had one valid output. So the composition g composite f only has a single element in it. If we didn't have this element there, if this one were undefined, we would say the complete composition is undefined. But as long as we get at least one valid output, there is an answer there. So let's take a look at what happens if we have algebraic expressions then. Instead of just ordered pairs, let's find f composite g of x and g composite f of x if these two functions are used. So to find f composite g, we start with g of x and we plug it into function f, right? So g of x is this equation, x squared plus x minus 1. Now we're going to plug this entire equation into the function f wherever we see the variable x. So this whole thing right here is going to go right here into function f. and then we tag on a plus 3. So this is f composite g of x, and then combining our like terms, we get x squared plus x plus 2. So that is f composite g. Now let's look at g composite f. For this one, we're going to start with the function f and put it into function g. So the function f is x plus 3. Now we're going to put x plus 3 into function g everywhere there's a letter x. So we're going to get x plus 3 quantity squared plus x plus 3 minus 1. Now we have to use FOIL to multiply this out. So you're going to get x squared. Don't forget your outer inner. It's going to be plus 6x plus 9. And then plus x plus 3 minus 1. Combining your like terms, you end up with x squared plus 7x plus 11. So f composite g is this, g composite f is this, and notice they are not equal. And we're going to go one step further now. Our next part of the problem says evaluate these composition functions when x is equal to 2. So then we're going to take f composite g of x, which was this thing, okay, and plug in the value 2 everywhere there's an x. So we get 2 squared plus 2, which is equal to 8. Likewise over here, we're going to take g composite f of x and plug in a 2 for x. So we'll get 2 squared plus 7 times 2 plus 11, which gives us a total of 29. So there you have it for this video. See you next time.